Welcome once again to the Simpkins Physics Corner AP Physics. Today it's all about projectiles, horizontal and angled. Let's remember our last lesson, the projectiles concepts lesson. We learned that the horizontal motion is always constant because there are no forces going to the left or to the right once you chuck something up into the air. So if I chuck this thing up in the air and it's flying through the air, once it leaves my hand, there's no horizontal forces acting on it, so it's going to have constant velocity in the horizontal direction. Or we could say Vx is going to be constant. When it comes to vertical motion, since there is an unbalanced force acting, that is the force of gravity on the object, that means that there is going to be acceleration, and gravity is what causes that. And then we had this idea in mind that although you are moving both horizontally and vertically at the same time, simultaneous, those motions are independent, meaning if I turn up gravity or turn it down, that's not going to impact the horizontal speed of my object, and vice versa, the horizontal speed of my object is not going to make gravity pull on it less or anything. So keep those ideas in mind as we make some observations. First, let's take a look at this one. This is just a nice little illustration of this principle that for projectiles, the horizontal velocity is going to stay the same, the vertical velocity is going to change because of the acceleration due to gravity. So watch out what happens. Orange is the overall velocity, and red is our Vx, which we call the x component of the vector, and the Vy is the vertical component of the vector. Watch what happens as it goes up in the air, reaches the top, and comes back down. Through that whole flight, you see what's happening here with components of vectors. And we're going to be talking about those today. If you wondered why we spent so much time on trig and vectors last week, it's because we needed those tools for today. So if you look at this, what we see here is that the Vx stays constant. The green Vy is going to decrease because gravity is down and therefore the acceleration is down. So it's going to slow down on the way up and it's going to speed up on the way down. The whole time Vx didn't change because there was no horizontal force, but Vy was always changing because of that acceleration due to gravity. So that's our first little example I wanted to show you. And here's a second example, another thing we can observe, just a general principle for projectiles. If you shoot a bunch of projectiles up in the air, and here's the caveat, if they all are launched with the same launch speed. So let's say I have a cannon that consistently fires the same launch velocity out of the cannon, right? Okay. If it's the same launch speed every time, then there's an interesting thing that arises when we consider the angles that these things are being shot at. All right, I have to get rid of this guy so maybe you can see it. Oh, here it is. Up top here, you see they're labeling the yellow path is 15-degree angle. The green path is a 30-degree angle. The blue path is a 45-degree angle. The purple path is a 60-degree angle. And the last one here is going to be a 75-degree angle. Now you'll notice the 75-degree angle one stays in the air the longest. It has the longest what we call hang time. All right, and it also reaches the tallest overall height, of course, because we shoot it mostly up, as opposed to the 15-degree one, which we shoot mostly out. What I want you to remember here, though, is that there's this cool little thing that happens. First of all, here's the first thing. The longest distance for the projectile's launch, again, if the cannon, the launch velocities are all exactly the same coming out of the cannon, all right, I'm not talking about components, I'm just talking about the firing speed out of the cannon. If it's the same, 45 degrees is going to get you the longest shot. Then working backwards from there, look at what happens. 60 and 30 land in the same place. Oh, 60 plus 30 is 90. I call it the 90 rule. If two angles add up to 90 degrees, then those two shots are going to land in the same place. Look, 15 plus 75, they add up to 90. They land in the same place. So a couple of cool rules there. If the launch velocities are all equal, then that angle rule will pop out. 45 will be the longest distance, and those two angles that add up to 90 will land in the same place. Now they'll get there in a different amount of time, right? The one that goes the highest will take the longest to get there, and the one that goes really low will get there really fast, but they will land in the same final location. So just something to keep in mind as a little concept thing. Let's look at problem solving for today. Today I'm going to show you the strategy of an XYT table. And I call it XYT table because, one, you can see this T that separates it when I organize it, but two, it's because T is key. You see, the time is key. This concept of, okay, we got different stuff happening in the horizontal direction, that's constant velocity, and we have accelerated motion happening in the Y direction, but they both happen in the same amount of time. They're happening independently but simultaneously. So in the Y direction, we got all these crazy equations we got to use from our equation sheet. In the X direction, it's just a constant velocity. So let's take a look at the easy one first. Damien is parkouring across a rooftop. If he starts on a building that is 100 meters high and wants to land on the roof of a building that's 80 meters high over here, How fast must he run to clear the gap? So remember, the first thing you want to do is set a coordinate system when you begin a physics problem. I'm going to define the second rooftop, my x final, as 0 meters. But Mr. Simpkins, it's 80 meters tall. Yeah, but I get to define the origin because that's how it works in physics. I also get to define which way is positive. I'm going to make to the left positive because I don't feel like dealing with a negative velocity there. And I'll make up positive as well. So that's our coordinate system for this one. Now, what that means is if my final position is 0 meters, and what I should be saying is the y, because we're talking about the vertical position, then that means the y initial is going to be 20 meters. Now, if up here is 20 and down here is 0, that means positive is up. That means that the acceleration in the y direction is going to be negative 9.8 meters per second squared. Any other information we need to know? Oh, we also know about x. Ah, man. That means we got to separate everything. So what we do here is we make an x, y, t table. We put the x stuff over here. We put the y stuff over here. And it turns out I'll make my x initial 0, and I'll make my x final 8 meters. Okay, so this is our information that we have to start with. Now it says, how fast must he run to clear the gap? So how fast must he run? You notice that he's just running off of the building. We're keeping it easy for now. He's not jumping off the building. He's just straight running off, just YOLO, all right? And if that's the case, then that means our v initial y is going to be equal to 0. Why? Because if you're running perfectly horizontal, you're not jumping up, you're not falling down right away, your initial up and down speed is 0 because you run straight off. And then that we're going to use to figure out what is the Vx that he needs to be traveling at in order to make that work. Okay, so let's jump into it. Now you might notice we don't know anything about time on either side, but remember, t is key. So is there a way that we can get t from one of these sides? It's probably not going to be the x side because I only know the positions. I don't know the speed and I don't know the time. That's not looking really good. But if we consider our equation sheet and we look at some of these equations that we have to pick from, consider the second equation on our equation sheet, which, a reminder, looks a little something like this. And if we take this equation from our equation sheet, we notice that these problems where you just run straight off the roof are a lot easier. Why? Because your initial up and down speed is nothing. And so that cancels this whole term in the middle. Why? Because 0 times t would just be equal to 0. And so what we could do here is plug our numbers in. We could say 0 equals 20 meters plus 1/2. All right, now remember, up is positive, so that means we got to do our negative 9.8, and we do the t squared there. Okay, so subtract 20 from both sides. Negative 20 equals negative 4.9 t squared. Divide both sides by negative 4.9. And then we'll have to take whatever that is. We'll have to take the square root of whatever that is to get it equal to t. So let's do that on our calculator. Boom, 2.02 is going to be the time. Now you're like, Mr. Simpkins, that doesn't tell me how fast he has to go. Ah, but here's the key. The key is t. You are falling down as you move out. And so if you are falling this far for 2.02 seconds, that means you're also moving this way for 2.02 seconds. And so what I'm going to do is I'm going to put the t over here on the x side of my information. T is 2.02. And then I'm going to scoot down here to finish it up just because this is where I have the room. If velocity is equal to delta x over t, then I can determine what velocity I need to run by just doing my change in velocity, which is 8 meters over 2.02 seconds. And that's going to get me 4 meters per second. So our final answer, our final velocity for this one, sorry, whoa, my PowerPoint is having a seizure here. Okay, let's see. There we go, is 4 meters per second. Okay, so that's how we would do it. It's called a horizontal projectile problem. Why? Because you just run straight off there. All right, so you're traveling horizontally. Now, I was going to do this, the rock problem, but I'm just going to post this as an ancillary thing in video. Same exact strategy. It's looking how fast would you have to run in order to jump into the window from that famous movie Skyscraper. Because I want to get to talking about angled projectiles today. Angled projectiles are defined as projectiles that are launched not straight off of a roof, but up at some crazy angle. A couple of points you want to be aware of is the very tippy top. We call it the apex. And oftentimes they'll refer to how far horizontally you travel as the range. So let's look at a quick example of one of these. A golf ball was hit into the air with an initial velocity of 4.47 meters per second at an angle of 66 degrees above the horizontal. How high did the ball go? So up here. And how far did it fly? So here you go. Here's your apex and your range. Now, the tricky thing about angled projectiles, there's only one startup step, if you will, that you have to keep in mind. Okay, we're still going to use the same strategy. We're still going to do an x, y, t table to separate everything, but we have to break things into components. Y sine, he's back, all right? Remember, the y component of a vector, that is relative to the horizontal here, is v sine theta, and the x component of the vector is v cosine theta. So before we start our problem, we have to break this 4.47 cosine of 66. Make sure you're in degree mode or you get all the wrong answers. So this one's going to be 1.82 meters per second. And our Vy, I'll call it the Vy initial because that's at the very beginning of the problem, 4.47 sine of 66. That's going to be, Vy initial is going to be 4.08 meters per second. All right, so there's our components of velocity. Now we don't know a whole lot else, do we? We know that the acceleration is negative 9.8 meters per second squared. And that's all we get. Wow, how am I supposed to figure out how high the ball went with this information? Well, something very special happens at the apex. What happens at the apex is that you stop moving up or down for a second. Now you're still moving horizontally. You don't just fly up in the air and freeze right at the top, right? But at this very top here, you have a y velocity of 0. So that tells us y velocity equals 0 at the top. Okay, that's important. My PowerPoint's flipping out on me again here. If it says how high did the ball go, I'm looking for the y. Okay, how high did it go? How high did it go? How high did the ball go? I'm looking for that one. So what I'm going to do here is I'm going to call positive up and to the right, and I'm going to call this initial y 0. And if I do that, you'll see that there's only one equation that works with all this stuff that I have right now. And it's kind of a funky one. It's Vy squared equals Vy initial squared plus 2a y minus y initial. All right, so I'm going to assume that you guys can plug things in and do algebra. So I'm going to wave my magic wand and show you the next few steps. Okay, magic wand was waved. All I did was take the equation, plug in the values from our list up there, do some algebra, and that got me how high did the ball go and how far will it fly. Well, it got me how high will the ball go. Now we want to do how far will it fly horizontally. So let's take a look at the other direction, in the x direction. So remember, t is key. Let's see if we can get t. Guess which side I'm going to use? The one with a ton of information. Okay, so there's probably multiple ways to get t here. I think the easiest way is probably if you're going to use this equation. It's going to be v equals v initial y plus a t. Okay, let's check that one out. At the apex, our speed is 0. Our initial speed was, in the y component, 4.08 plus negative 9.8 times t. All right, so we do some quick algebra, and we'll get our time that it takes to get from the starting point to the very tippy top. So if you solve for t appropriately, you would subtract 4.08 from both sides, and then you would divide both sides by 9.8, and that would get you a time of 4.16. Now, what does that time describe? That describes how long it takes to get from here to here. And that's called the apex time, or how long it takes to get to the very peak. Well, the thing is, what goes up must come down. So I have a question for you. If it takes 0.416 seconds to get all the way to the top, how long does it take to come back down? Answer, exactly double that. So here's where t is key, but you have to use that idea wisely. The time it takes to come back down is going to be the same amount as it took to go up. So the total time we were traveling horizontally is double that. So whatever 0.416 times 2, we're looking at 0.832 seconds. And now when it says how far did the ball travel, well, we know that velocity is displacement over time. And we can plug some things in here. So we can say that velocity, 1.82 meters per second, equals delta x divided by 0.832. And of course, we just multiply both sides by 0.832. So 1.82 times 0.832, that's going to get us 1.51 meters. So our answer for the displacement, how far did we go, is 1.51 meters. Don't miss the big idea here. Still independent and simultaneous. The x and y directions are solved at the independently, but that time can come from one side to the other. Just keep in mind when you go up into the air, you might have to adjust and strategize a little bit. If we can figure out how long it takes to get to the top, then we can double that to get the total time we are traveling in the horizontal direction. All right, well, I'm Mr. Simpkins in the Simpkins Physics Corner. Check out your practice sets for projectiles, and stay tuned. I might drop some bonus content with some extra projectile problems to give you even more practice. So until next time, this is Mr. Simpkins in the Simpkins Physics Corner.